Hello, my name is Mahesh Kumar. I am a second year student of MSc Chemistry. In this video, I will explain how to generate X-ray in X-ray tube. Firstly, we will talking that why we use only X-ray to study the crystal structure. Not other type of radiation we use like UV, visible, IR, etc. The answer of this question is that when we study the crystal structure, actually we study the diffraction pattern. So to get the diffraction pattern, or we can say to achieve the condition of constructive interference, the order of the wavelength of incident radiation is must be equal to or nearly equal to order of the interference distance. The order of X-ray and the order of the interference distance, in case it will have is same in case of X-ray. They both have same unit, basically unit of angstrom. Now coming discovery of X-ray. German physicist Wilhelm Röntgen accidentally discovered X-rays 1895 while working in his lab with a cathode ray tube. He noticed a nearby fluorescent screen glowing even when shielded and realized a new type of unknown invisible radiation was passing through materials and casting shadows. He named them X-rays due to their unknown nature. Characteristics of X-ray. X-ray have very short wavelength, have no charge and no mass, have ionizing ability, and have absorption and penetration power. They can pass through materials like skin, wood, paper, but are absorbed by dense substances like bone and lead. Procedure for X-ray generation. For experimental setup, we should have three type of component. First is electron source. Second, high voltage supply. Third is target, means anode. In electron source, we have cathode. Cathode is made up of a tungsten filament is heated by passing current. As a result, electrons are emitted by thermionic emission. These free electrons form an electron cloud near the cathode. Then we apply high voltage, usually 30 to 150 kilowatt. They accelerate the electrons in high voltage. They accelerate the electrons in between cathode to anode in high kinetic energy, with high kinetic energy, and then and the, this electric and this electric potential accelerate the electrons towards the anode target at very high speed. The anode target generally made up of high atomic number metal, commonly tungsten, molybdenum, copper. When the high speed cathodic electrons strike the target, means strike the anode, two things happen at near the anode. Most of the energy, approximately 99%, is converted into heat, means 99% of the kinetic energy is converted into heat, and a small fraction, almost 1%, produces X-ray. See in figure 1, we have cathode and anode. Electron high energetic electron beam generate from an cathode and goes towards the anode and towards the anode. Basically, here we have an anode rotor. And why we use here anode rotor? Because we have limitation of hot cathode tube. Because one limitation of hot cathode tube is that the target will melt if the strike current if the current striking the target is too large, because we strike the high amount of electrons with high kinetic electrons with target. So one way to enable to use of large electrons current is to use a design called a rotating anode, in which the target is spinning metal ring. In this design, only a small part of a spinning anode is struck by the electron beam at any one time. Basically, in the design of a rotating anode, basically basically we have increased the heat capacity of a spinning metal ring to avoid this problem. When we generate the X-ray in X-ray tube, we get two type of radiation. First is white radiation, yeah, Bremsstrahlung radiation. Second is characteristic radiation. Uh, when incoming electrons are decelerated by the strong Coulomb field of the target nuclei. As a result, as a result, the produces the photon. This means this sudden slowing produces photons with the continuous range of energies. Means it generates broad spectrum. Uh, Brimstone radiation is also known as white radiation because it contains almost all type of radiations like white radiation like white radiation. It is happen near the anode anode because anodic atoms repulse the anodic atoms electronic cloud repulse the cathodic electrons, and as a result slow down the cathode electrons. As a result, energy high kinetic energy converted into photons, and small fraction of energies provide almost 1% provide uh, generate X-ray. Then second is characteristic radiation. If a high energy knocks out an inertial electrons of the target atom, as a result vacancy is created. Then outer electrons falls into the vacancy. Energy difference is released as a photon. This photon has a characteristic energy unique to the target element. For example, K alpha and K beta lines. What is K alpha and K beta lines? We will discuss in next slide. See in figure 2. See in figure 2. These are the K alpha, K beta, K gamma, and see what are the K alpha, K beta, K gamma, A alpha, L beta lines. We will discuss in next slide. And what is the dependence of wide radiation and characteristic radiation? The intensity of the spectrum of wide radiation depends on the voltage used to accelerate the electrons, but is largely independent of the composition of the target. See in figure 3. When we increase the voltage, the intensity of the X-ray will increase, but the energies of the characteristic X-rays are independent of the voltage, but depends on the composition of the target. Means composition of target means composition of the anodic metal. Different metals have different type of characteristic wavelength, and because different metal have different type of energy gap delta E value. In crystallography, in crystallography, the now outdated Simon notation is still used to assign the symbol of characteristic X-ray. Here, principal quantum number and K, L, M, and they both represent the shell number. Here, K is corresponding to first cell, L is corresponding to second cell, M is corresponding to third cell, and N is corresponding to fourth cell. And azimuthal quantum number represent the subshell. See here. This is transition from 2 to 1, 3 to 1, 4 to 1. Transition means 2 to 1 transition is corresponding to K alpha line. Generate K alpha line. 3 to 1 transition generate K beta line. 4 to 1 transition represent K gamma line. And what is the alpha beta? What is the subscript alpha beta gamma? The subscript alpha beta gamma represent these significantly different energies that arises from the filling the same cell vacancy. It means energy of K alpha, K beta, and K gamma lines is different. Energy is different. However, they all transition fill the same frequency means same cell one means K shell. because, because this transition is K alpha transition is and 2 to 1, K beta is 3 to 1, K gamma is 1, because an energy gap between these energy levels is different. That is the reason the energy of K alpha, K beta, and K gamma energy of these lines is different. And what are the selection rules for transition? For allowed transitions, delta L means as difference of azimuthal quantum number is must be equal to plus minus 1. For forbidden transition, delta L is equal to 0. Uh, Delta is equal to plus minus 1 means transition from S to P, P to D, D to F is possible. Only this transition are possible. But S to S, P to P, D to D means 3S to 2S, 3P to 2P transition is not possible. These are the forbidden transition. That is the reason. That is the reason to because that is the reason to we have discrete spectrum and sharp lines because in characteristic X-ray we have selection rule. Uh, L radiation is generally not used for X-ray diffraction experiment. Mostly because the yield of L radiation from a hot cathode tube is much smaller than the yield of K radiation of the same wavelength. In crystallography, the two most commonly used X-ray beams consist of either copper alpha K alpha, molybdenum K alpha. Copper atomic number 29 produce high wavelength means less energy X-ray in comparison with molybdenum, because molybdenum produces high energy wavelength because high energy X-ray because it have a short wavelength. And what are the reason behind it? Because the energies of the characteristic X-ray increases as the atomic number of the target increases. It will happen because uh, when we increase the atomic number, effective nuclear charge increases as that cause the cell contraction. As a result, energy between two energy levels, energy gap between two energy levels will uh, uh, energy energy gap between two energy level will decrease, and as a result we, as a res- energy energy increase energy increase. As a result wavelength is increase. So here molybdenum has energy sorry energy between two energy level energy gap between two energy level will increase. As a result wavelength decrease. So here molybdenum have less wavelength than copper. Yeah, then copper radiation is more useful if the unit cell is large, such as protein crystal, because copper have large crystal. Because order of X-ray and order of interference is almost same. Same as molybdenum radiation is more useful if the unit cell is small, because molybdenum have smaller wavelength. Here K alpha 1 and K alpha 2 lines is nothing but 2p to 1s transition is labeled K alpha due to spin angular momentum and orbital angular coupling. Spin angular coupling line is actually split. Is K alpha line is split into two closely spaced components called K alpha and K alpha 1 and K alpha 2. Filtering of X-rays, generation of monochromatic beam. Why we use filter in generation of X-ray? Because K alpha 1 and K alpha to produce because to produce the monochromatic beam. K alpha 1 and K alpha 2 lines differ by less than 1%, so they act as a single monochromatic wavelength in X-ray diffraction. However, K alpha and K beta differ by about 10%, producing a separate overlapping pattern, making it harder to measure accurate intensities. It is make it harder to measure the accurate diffraction patterns. Since K alpha is stronger, filters are used to absorb K beta and obtain a nearly monochromatic K alpha beam. We are using filter based on following principle. X-ray generated from a target with atomic number Z. A good filter to remove the K beta radiation selectively is a foil with atomic number Z minus 1. For example, neobium 41 is a good filter for K beta radiation of for molybdenum source Z42. And why and the clear explanation I will explain in next slide with pictorial explanation. And another way to generate an X-ray beam containing only K-alpha radiation is to use a monochromator. Here we use diffraction grating by selecting the diffraction angle corresponding to K-alpha radiation. A monochromatic X-ray beam is obtained. This is the pictorial explanation. Figure 5 represents the absorption of X-ray. This pictorial explanation gives clear idea about filter, how to choose filter and why use choose filter. Uh, Figure 5 represents the absorption of X-rays by copper. When we decrease the wavelength, basically energy of the X-ray will increase. Means most of the energy will pass through. Simple. Means absorption will decrease. But at certain time, but at some time, when we continuously decrease the wavelength, X-ray getting sufficient energy to knock out the K shell electrons. Means in graph we observe abrupt change in absorption. This vertical line shows the abrupt change in absorption. This vertical line is known as K absorption age, and this K absorption age is more useful in to choose the filter. For example, in figure 6. Part A represents the copper X-ray. This graph, part A, copper X-ray emission spectrum containing both wide radiation and characteristic lines. The thin gray line shows the X-ray absorption spectrum of a nickel foil. This thin line here, absorption age of nickel is exactly fallen between the line of K alpha and K beta K alpha and K beta line of copper source. As a result, nickel foil absorb the K beta lines because the energies of K beta line of copper source is exactly equal the energy of K beta line of nickel. As a result, as a result, see in figure 6 of part B. This figure is represent the resulting copper radiation spectrum after filtering by absorption with nickel. The K beta radiation is strongly absorbed and K alpha is mostly transmitted. This copper K beta is intensity of this line is will decrease and intensity is increase. Basically, copper beta lines will absorb and copper cable line will transmit it. Uh, Basically, we get almost monochromatic beam. Hence, for good filter element, foil absorption edge must be fallen in between the K alpha and K beta lines of the target element. Then, what is synchrotron? Synchrotrons are evacuated pipes curved into a these are the synchrotron curved into a large ring that is tens to hundred of meters in diameter is a type of particles accelerator. Basically, it accelerates the charged particles, usually electrons, to nearly the speed of light using radio frequency cavities. A strong magnetic field bend the particle in a circular path. When these ultra-relativistic electrons are bent, they emit extremely bright electromagnetic radiation from infrared to hard X-ray. These radiation collected and used in experiments such as X-ray diffraction spectroscopy imaging. Basically, we use synchrotron to produce the X-ray, high energetic X-ray beam of X-ray. The emitted synchrotron radiations are highly intense, highly collimated, tunable. You can choose the exact wavelength, the energy. Why we need a synchrotron instead of a hot cathode X-ray tube? Because for a very small crystals, in less than 0.5 millimeter, a weakly scattering sample, for example, proteins, nanocrystal, the diffraction signal is too faint to collect useful data. That is the reason we use synchrotron in the place of hot cathode tube. because hot cathode tube sources produces relatively weak X-ray. Uh, Synchrotron provide extremely high intensity beam that can generate measurable diffraction from tiny or weakly diffracting crystals. Tube sources give only fixed wavelength like copper k alpha, like, means copper k alpha, molybdenum k alpha 1.5 or 0.7 storm. Synchrotron radiation is continuous. You can select any wavelength using a monochromator. This is crucial for anomalous dispersion method. Means multi-wavelength anomalous dispersion, single wavelength anomalous dispersion in crystallography, where you tune the wavelength near an absorption edge of a specific atom. Absorption edge is more important. Absorption edge is very important in the to choose this specific type of wavelength. And what are the anomalous dispersion method? In X-ray crystallography, one big challenge is the phase problem. We measure diffraction intensities but not the phase. Basically, we want to measure diffraction intensities to study the crystal structure. In anomalous dispersion method, the synchrotron tunable X-rays are adjusted to wavelength near the absorption edge of specific atoms in the crystal. These enhances differences in scattering from those atoms, which helps solve the phase problem in crystallography. Okay, and then thank you.